So there is a class forum that's been opened, and I think about 22 people have already signed up. I don't know, I'm assuming that is still registered. I mean, there's been bunches of, obviously, as I said, registration changes. So make sure by the end of today, if you are continuing in the class, make sure that you join this forum. For now, I essentially just made it to be, to get there. I think for those of you who were registered as of the time when I sent that mail, you got an email with the address to the forum. If you don't have that email, if you registered afterwards or some such thing, then if you go to the home page for the course, there is like a link to the class forum here or here, whichever you click, you'll get there, and then you do join now thing. And then for now, I'm just basically, until everybody registers, I'm just leaving it open. You can all join, and after that, I'll just make it moderated so that new people can join without my permission. And then this is meant for essentially discussing anything related to the course. There was actually, in fact, there is one long discussion that's going on. Actually, I just asked a couple of questions, and then a whole bunch of people had answers and so on. So I asked, do you know of any learning techniques that operate at the atomic level, and does the idea even make sense? And then I also asked, can the world be same world be ergodic for one agent and non-ergodic for other? This was mostly I just asked so that there would be something to discuss. But pretty much anything you want to talk about, you can put up there. It's completely open for you guys. And this is actually, it does have the upvoting, etc. as far as I can tell. If you're logged in, I believe you can actually upvote things. Yeah, see, you can upvote things. So I always wanted to, as I was mentioning to some of my colleagues, I always wanted to run a forum where I would be dishing out karma points because actually I'm allowed to give karma points. I'm from India. The rest of the forums are not. So, basically this is one way of actually figuring out what questions people have. It's a small enough crowd that probably every question you have I will answer to the extent I can. But in particular, one of the things apparently that was very helpful for these massive online courses was because clearly no human being can actually answer 10,000 people's questions. So you just have to hope that somebody else also has your question. And then they upvote your question. And then if enough people have it, then we will support that. But we can also use it in terms of if you found some colleagues' explanation particularly helpful for you, use the upvote, and I can use this as some sort of a participation thing in the end. But in general, use it constructively. Try to. I cannot force you guys, but I think it's very useful for to use. I will set up an email list too, and any important announcements I will send on the email list. They'll also probably get posted here, but they will certainly go by email. I'm not making an email list until, as I said, end of today, because then we'll know exactly who's actually in the class. Okay, any questions before we go? Okay, so did anybody, there was interesting discussion at least on one of these things, which is, do you know of any learning techniques that operate at the atomic level? Does the idea even make sense? That's actually, does anybody, there was some discussion, and did people have any other comments on that? See, when you followed the discussion, you just take my word. So to understand atomic propositional, this is the last slide that last but one slide I was mentioning, we were discussing last class. Apart from our in basically supporting a generally intelligent agent which has more and more expressive actions, more and more sophisticated goals, and less, not less and less necessarily, but partial perception, because partial perception makes things hard, and also environment which is dynamic. That's basically where, you know, it becomes more and more like real world. We are interested in finding techniques that would support those, and I try to say, put a spin on the 471s. There are lots and lots of different intro to AI courses. Everybody does a slightly different one, but one least common denominator that everybody has is they will at least know after intro to AI how to support deterministic actions in a static world with full perception and goals of attainment. Okay, if you don't know that, then I mean you didn't do anything in intro to AI at all. Okay, and then basically people will, you know, consider expanding it in slightly different directions, but that's the minimum that we have looked at. Then having considered, let's say, any specific agent. So one aspect in this course is, if you think in terms of intro to AI. So here was simple agent. I put it in quotes because simple agent, as I said, itself is actually quite hard to control in terms of the amount of planning required to support. The complexity of reasoning is high even when you have deterministic actions, static worlds, and goals of attainment and full perception. Okay, so if this is 471, we want to go towards, for example, goals. The first thing that we want to add is goals as reward functions plus stochastic actions. That's what we're going to discuss today, actually, starting today. Okay. Now, of course, there is a separate orthogonal dimension which you want to keep in mind too, which is for any specific agent, you can first consider atomic model. So the atomic model basically means states are indivisible. That's what we discussed last time a lot. Okay, and you need to at least understand how does an agent like this live in atomic model. Okay, in 471, atomic model, A star search. That's what you did. Okay, A star search is basically what you can, what you need to understand to support deterministic action, static worlds, perception, full perception, and goals of attainment. Okay. We also considered in 471, in intro to AI normally, you also considered propositional representations. With this stuff I discussed very quickly last time. I'm slightly elaborating on that because I think it's important, because it gives you a feel for, you know, how the investigations would be focused, you know, how we would focus our studies. Okay, so in the propositional representations, the states actually have structure, internal structure. Okay, and we'll assume that in the propositional representations that the states are made up of state variables, or if you're a logic person, made up of propositions. Okay, which are just statements that can be true or false. And that in itself cuts down the size of the memory required to just put the whole entire state space in. Okay, in essence. Okay, and as I was mentioning last time, if you have n state variables, then you can get 2 power n states. Or equivalently, if you have s states, you can get with logarithm of s as the representation. And that's a good thing. Okay. Now, of course, while it is a good thing, it also makes life harder in terms of actually doing the reasoning. Okay. In the context of atomic models, all the agent had to do is to figure out which state it's in, it does an action, and then it gets to some other state. Of course, it cannot For each action, it only gets to go to one specific state because of the deterministic actions I said here. So I do action A1, start with S0, I'll get S1, if I do A2, maybe I'll get S2, and then basically look at this graph and then figure out where you reach the state that has goal satisfied. Okay, that's all you need to do. Whereas if you have propositional representations, now actually you have to look inside the state to see whether or not the goal conditions are actually satisfied. Okay, and furthermore, since you know the structure, you want to exploit it. Notice that you can always, if people give you propositional representation, you can say, I don't want the propositional representation. I can compile it down to atomic representation and live there. Okay, one way of thinking about it is a loose analogy, although it's not a great analogy because it breaks in some places, is this is assembly language. And this is your C++ sorts of languages. Okay, eventually you essentially do actually compile it down to atomic models, right? In assembly language, all the things ultimately get done at assembly language level. Okay, so you can compile it down, but the advantage, actually there are two advantages. One is the propositional representations are going to be much smaller, so in fact you can decide whether or not the model makes sense if you are writing the model. Okay, it's much harder to ensure that an atomic model is correct. It's somewhat easier to ensure that a propositional model is correct. Okay, and then the other interesting thing is not only do you want to represent propositionally, you also want to reason propositionally. Like I said, you can always represent at a high level, and if you don't feel like doing the reasoning at the higher level, you compile it down to state space level. This actually gets done, as we'll see as we go through the course, that there are many situations where people will allow you to specify models at the propositional level or relational level, but will wind up doing the reasoning at the atomic level or the propositional level. Okay, and so then basically what would be more useful is to do the reasoning itself at the higher level. And typically doing the reasoning at the higher level means the algorithms will be more complex. You see what I'm saying? I'm talking about some general abstract points, but they all have instantiations for every specific problem. Okay. So for the propositional representation in 471, we looked at strips planning. Or SAT, for example, satisfiability problems. Those were at the propositional representation. You can go higher. You can go to relational representations. Notice that when you did strips planning, essentially strips planners were doing a star search. And they could actually have decided to convert the entire strips planning problem into an extensional A star search problem and let it be solved that way. But there are arguments saying that in fact if you do your reasoning at the higher level, you can actually be, you'll be able to exploit the structure of the state much better. Okay, this is actually one of these tricky issues. While theoretically, in theory, it should be the case that you would like to do reasoning as well as representation at the same level. In many situations, actually current algorithms represent at a high level, do the reasoning at a lower compiled level. Because we just happen to have very efficient algorithms for the compiled level. Okay, why isn't there a C++ machine in computer science? Those of you may know that for a while people used to have Lisp machines. It's long before you, I guess. These were heavily micro-coded machines that would support Lisp directly. Okay, and in fact, for a while in computer science, in the hardware, in computing, the direction was to come up with more and more micro-coded machines that will support specific automatic, high-level languages. Okay, but then people sort of gave up on that and then went for RISC instruction set, one reduced instruction set, and everything is just compiled down to this. Now, theoretically, it's not at all obvious that compiling it down into the risk set at any given point of time would be better than at that point of time supporting the micro-coded language. What people were able to see is that if you were to just decide on one substrate, the RISC architecture, and then Intels and Motorola's can just keep working on improving that architecture faster and faster and faster every year. Okay, so even though at any given year, if you gave like a competition for both X and Y, saying, in December we're going to have this benchmarking competition, either you can come up with a micro-coded support for C++ or direct support, or compiled support for C++. It's likely that the micro-coding will win. But there are so many different languages, and how many different architectures are you going to develop? Whereas if you just compile it down to machine language like the RISC or something, then basically somebody's life would be just improving that particular substrate, while other people will still write programs in higher level language because it's easier to write them there. You see what I'm saying? So, and this happens in AI too. It turns out that although nobody actually honestly believes that compiling, going after having got to factored level, compiling it down to state space level would make sense. Nobody believes that. I'm sorry, I kind of use a double negative, but nobody believes that if you have strips planning, compiling it down into A star search would be a good idea. However, if you go to relational level, okay, in 471 made it predicate logic. Okay, and predicate logic can basically allow it makes your life simple because you can write fewer rules in predicate logic than writing large number of state variables, because you're talking about relations between objects. And then on top of predicate logic basically is first order representations. And there you not only have predicate logic, but you also have quantifiers and functions. And a great way of seeing the power of the higher level of the language is to see that if you were to try and write chess, the theory of chess, it's a deterministic, basically a deterministic game, especially if you assume opponent away for a minute. Okay, the number of chess states are how many? The number of chess states are known to be something like 10 power 157, which is way more than the number of atoms in the universe. Way, way more. Okay, so you cannot actually write, seriously speaking, you cannot write a state space model for chess on any little book. Okay, propositional models will be only logarithm of 10 power 157. Even that is too high. If you write chess game rules in first order logic, it will be a couple of pages. In fact, half a page. That's the power of higher level abstraction. The question is, do the chess machines actually reason at this level, or at this level, or at this level, or at this level? That part is in fact, the state of the art in AI is that in fact, in many cases, the current best algorithms wind up writing at these levels, but certainly compiling down to propositional level. Not necessarily to state space level, but to propositional level. A classic example, so for example, the best ways of reasoning with predicate logic and first order logic expressions these days is still converting into SAT solvers, converting into SAT reasoning. SAT is basically propositional logic. Why? Because just as there is an Intel and a Motorola for risk machines, risk architectures, there is an entire community called SAT community, whose only interest is to come up with faster and faster and faster and faster and faster SAT solvers. Every year they come up with even faster SAT solvers. And they're learning all sorts of extremely interesting theoretical points as well as practical points about what makes an efficient SAT solver. And we are talking here about millions of variables and multiple millions of clauses in SAT. Again, I'm assuming that in SAT, essentially you have a bunch of propositions, P, Q, R, S, etc. These are called also variables. And then the clauses would be saying they can take true or false values. And if there are no constraints, you can just give them any value and you'll be fine. But I might give you constraints saying if P and Q, then R must be true. That means if you were to give true to P and true to Q, then you must give true to R. There's no other way. So they will wind up constraining the valuations you give for different variables. And these are called clauses. These are the constraints and these are the variables. And SAT solvers currently can solve really, really large number of variables and clauses in, within minutes. That's exactly what happened on the Intel side too. The RISC machines of today are so much faster than the RISC machines of list machine era. Okay, so much so that, basically the current list, if you take that list machine era list machine and try to run a program on it in Lisp, that will still be orders of magnitude slower than running the same Lisp program on the RISC machine in a compiled fashion. You see what I'm saying? Okay. So the interesting thing is that, in fact, many people, the current state of the art is you will convert, you represent at a high level, but you do reasoning, you tend to do reasoning at the propositional level. There are a bunch of people who think this is a losing game. And so there is a lot of research that's going on which tries to support reasoning at the predicate logic, at the relational as well as the first order level. Okay? So in fact, there are people like, so as far as the working current state of the art in AI is concerned, you have to understand this. That, basically, you want to understand how to represent here. We will try to understand in some cases how to do the reasoning at the same level. But you also have to realize that many a time they just get converted down to here. Now this whole discussion is supposed to make you realize that if I were to give you any problem, you should first understand how to do it at least at the state space level. If you don't know how to do it at the state space level, then you don't know how to do it at all. Okay? And then think of how to lift it. There is this word lifting is actually used. Lift it to propositional level, lift it to relational level, lift it to first order level. Okay? To put one very specific field, one very specific subfield in AI, which is going through this particular kind of banks, it's probabilistic reasoning. Consider Bayes nets. Again, people who have done intro to AI probably must have heard of Bayes nets. What representation language or what level are Bayes nets? Atomic, propositional, relational, or first order? What? Propositional. Right? Bayes networks are at the propositional level. There are relational Bayes nets. Basically probabilistic relational models, Markov logic networks, and so on. Okay, I'm throwing names, some of which we'll actually cover, but I'm also assuming that since it's a graduate class, not only will I do some topics, but I'll also give you sort of rim view of a bigger area. Okay, so how do the relational Bayes networks and first, PRMs and MLMs work currently? It turns out the most obvious thing they do is to just compile them down to base nets. And then there are people who are trying to support base network inference directly at the relational level. The reality is currently the winners are the grounding guys, the guys who actually do it at the propositional level. That could be because we don't understand enough as to how to do reasoning at the higher level, or that could be because it will never be actually worthwhile to do reasoning at the higher level. We don't know. Okay, I mean that's the, so in fact graduate courses can be about areas that the teacher doesn't know enough about, the community doesn't know enough about. And this is one of the issues. That doesn't stop people from working on not only relational base nets, but also first order base nets. And in the case of research, basically multiple people can be looking at multiple different areas. Whatever works out will eventually, some of the things which are about to work out will get into the graduate level. And if they really work out, they'll get into the undergraduate level. Okay, so we don't even touch relational base nets at all in the 471 that I did, for example, which I think is reasonably ambitious enough. And first order, we don't even think of saying that word. And yet, you can talk about first order representations for deterministic, that is non-probabilistic knowledge. Because we do talk about first order logic in 471. So there is this other issue that when you go from deterministic to first order, everything becomes hard. Not surprisingly. Okay? And that typically you understand everything at this level, then hopefully here, and if you still live long enough, here and here. Okay? Questions about what I said? Okay. So with respect to this, what we'll be doing today is MDPs, which will be atomic models for agents which have goals as generalized reward functions, and actions are actually stochastic, they're not deterministic. That's the only two things we are going to do. You see what I'm saying? That's the only two things we're going to do. And in fact, then you can also throw in, so one of the things which we haven't extended here yet is additional agents in the environment. We also didn't, so here, no other agents and perfect perception. Perfect perception. So the next point, for example, could be all of these plus partial perception, partial observability. And if you do that, you would get what's called MDPs. Okay? And then you can say, well, I will do that as well as other agents. And this whole thing plus other agents. If you do that, you get DEC MDPs. Generally, life is not really worth living by about this time in terms of the computational complexity of the problem. Okay? Because what happens is the computational complexity of the problem in terms of just the states, in terms of the atomic states, is polynomial here, it is exponential to undecidable here. At the state level. Okay, now the interesting thing is, if A star search is polynomial here, will planning be polynomial at the propositional level, or higher or lower in complexity? This what? Okay, let's go with show of hands. Okay, how many people think it will be polynomial? 3, 4, 5. Okay, who thinks it's going to be lower? 1. Who thinks it's going to be higher? Okay. Why do you think it's going to be higher? Yes?
Well, because, I mean, if you take a propositional description of the environment and you make it atomic, you're going to get an exponential number of states.
So, the important thing to understand is complexity is measured in terms of the size of the input. Okay? Right? I can be polynomial at this level because the problem itself is exponentially large. But the same problem here becomes polynomial sized. So if I'm polynomial in the polynomial size, then I just got a sort of a Nobel Prize because I just proved P equal to NP. Right? Because polynomial times polynomial is still polynomial. Okay? So in general, the reasoning hardness increases this way. But you should not take that to be a bad thing. Do you understand what I'm saying? The reasoning hardness increases this way because the input is becoming smaller for the same problem, the problem that you have in mind. Let's say you wanted to solve chess. The chess problem will be 10 power 157 sized here. And it's only polynomial amount of work in 10 power 157, I'll solve the chess problem. And you shouldn't be very happy about it. Okay? Whereas if you come here, suppose I say I'll solve it in exponential time, that looks like a sad thing, except exponential time, but the input is already logarithmic. Because, you know, when you lifted the problem description to propositional level, it will be logarithmic. You see what I'm saying? So again, this is another thing that you have to understand. You know, when the complexity always just keeps increasing this way. It's because the input size keeps reducing, and what you care about is, you know, how hard is it with respect to the input size. Okay? So this is actually a good way to figure out, you know, a couple of things that you have done in computer science. I mean, why would anybody be doing this when the complexity increases? Because it's complexity increasing in a smaller word number. And it can still actually be a win in the end. Okay, so there's MDPs, POMDPs, DEC POMDPs. POMDPs itself will become, you know, exponential for finite horizon cases and undecidable for infinite horizon cases. And the two words, infinite and finite horizon, you will start hearing about it starting to in terms of MDPs. And then you get to DEC POMDPs. Now, one interesting question would be, should we be thinking, I mean, I have not actually put any technical slide yet, you know, and yet you can make a lot of sense at even a qualitative level. Should there be DEC MDPs? DEC, by the way, is decentralized because there are multiple different agents. Okay? Should there be DEC MDPs?
In theory, but they're less useful because you have multiple agents. They may not be aware of the other agent's actions.
So if there is no, if everybody's brain is held on their forehead and you can read what they're thinking, then it's actually there are no multiple agents to some level, right? Because, you know, partial observability is like the 101 of multiple agents. I have no clue what you're thinking right now. You know, some of you are actually giving me some clue by actually falling asleep. Others are making it look like you are understanding what I'm saying. But you learned how to behave in classes. You know, make teacher feel good for a while, at least, right? So I have no clue, and you know, it is partially observable world when you have multiple agents, and so computational complexity worsens even here. Even becomes much worse obviously. I mean, you would say, how can it be worse than undecidable? Well, even finite horizon case, it can be undecidable. And so, of course, then we will start doing all sorts of cases. Whenever we talk about complexity, we are talking with respect to optimal representations. Okay, just one second. But we will also consider approximate versions, approximate inferences on these cases to keep the cost low. Yes?
Now, with MDPs, POM MDPs, and DEC POM MDPs, those are all Markovian. Are we ever going to talk about non-Markovian?
Yeah, so there is a whole menagerie of MDPs. There is MDP, and there is non-Markovian MDPs, and R MDPs. So, for example, there is non-Markovian reward as well as non-Markovian dynamic MDPs. One of the interesting things is that non-Markovian reward and non-Markovian dynamic MDPs can be compiled back into MDPs. And in general, we'll assume that if a problem can be compiled into another problem with only a polynomial size increase, we don't care. It's the same problem. Right? Okay. And then there is another thing called SMDPs. One of the things we'll see in MDPs is we'll assume that the actions are instantaneous. But we saw as last class that actions have durations. So then if actions have durations, the MDP models are theoretically not enough. You have to generalize it to something called SMDPs, semi-Markov relation processes. And then you have this whole thing called POMDPs, DEC POMDPs, and the MMDPs are basically, again, you don't need to remember all of this. I'm just sort of giving you a feel for where the world is. But MMDPs are multiple agents, all of who wear their brains on their foreheads. In which case, MMDP can be actually compiled back into MDPs. So it's only an efficiency issue. Okay, so the answer is yes, there are all these things, and basically many of them, especially DEC POMDP onwards, they're pretty hard, even at the atomic level. If something is not polynomial at the atomic level, it's quite depressing, because then essentially that means it's a pretty hard problem. But then in AI, lots of interesting problems are actually non-polynomial at the atomic level. So MDP is probably the last time we get to see a nice problem that is definitely polynomial at the the inference case at the atomic level, because finding the optimal policy for MDPs is only polynomial in the number of states. It's only polynomial in the number of states. Okay, but the number of states, of course, can be very large. Okay. So, with respect to all this discussion that you may or may not have been aware of before, do you guys now I wonder, before I go off into the MDP discussion, does anybody have any idea as to whether learning techniques that you have done, do you know of any learning techniques at atomic level? So, we did A-star search in 471, so that's at atomic level. Planning is at the relational and the propositional level, and in fact, there are variations of SIMS planning that do relational, and normally, in fact, if you remember, from 471, you write these PDDL models for the domains, which are essentially relational models. Because when you want to write the model, you don't want to write many, many, many different actions. So, for example, if you have the simplest kind of a planning problem that people talk about is Bloxwald problem, and so you have A and a B and a C. And then you have like a hand, and then you can pick an action, pick a block, put it on top of another block, for example. So, if you were to write actions as in the propositional terms, then you have to have move A from B to C is different from move A from C to B is different from move A from A to A is different from move C from B to A. All of these are different actions. You have to write them all down, one after other after other. Right? Instead, what do? You write move X from Y to Z. And then describe the action at that level. And in fact, unbeknownst to you, most of the planners actually take that relational representation, make the action, get the relationally represented actions, but then do the reasoning at the propositional level. They ground everything. Just to be fast. Because there are faster reasoning algorithms at the proposition level. Okay, so this, for planning there is one at this level, one at this level, one at this level, and so on. My question is, do you guys know of any learning algorithms? Again, I have to act as if you know something about AI. Okay, so do you know of any learning algorithms that work at atomic level? What?
Relational.
Why is it the atomic level?
There's no structure in the...
No, but it has at least x1, x2, x3, x4. Okay, so this issue is what is structure of a data point? As I said in the discussion on the web, so if I give a point by its coordinates, that's not atomic. I have already figured out the features for the point. The way you would give that point in a state space representation is to say it's point number 10,975. Do linear regression on those kinds of points. Again, as I said, I want to look at you people and learn about who is understanding, who is not understanding. If I'm only given as your descriptions, your social security numbers, can I learn anything? I can certainly learn that the guy with social security number 918049234 seems to sleep most of the days. That I can learn. But then, what about the same number with the last digit being 7? Do I have any inference on that? No. You see what I'm saying? Learning works by generalizing, by removing some of the properties, saying those are irrelevant. Okay? Everybody who seems to not have slept last night will sleep today in the class. It doesn't matter what color of the shirt they're wearing, what is the, whether or not they have a water bottle in front of them doesn't seem to matter. None of those seem to matter. So if you give me representation of each of you in all these many coordinates, I can throw away all these irrelevant ones and say what matters is, did you sleep yesterday night? That's kind of more relevant. But that reasoning is being done at the propositional level, at the minimum. So I want you to be able to be surprised if somebody were to come and tell you that you can do learning even at the non-trivial learning. Of course, I did learn even with your social security numbers I can learn, right? I can say this particular social security number is bad seed, seems to be sleeping every day. But I can't generalize from beyond that. Learning is about generalization, right? So what kind of generalization can I do if I only have atomic level representations? It's kind of one of these things that you should be surprised at, but you are not, because as you and many other people said, and believe me, this is not at all a wrong thing to think, because most people think that way. Linear regression is not being done on unstructured data. It has structure. Okay, atomic means no structure whatsoever. And learning, not surprisingly, in 471, we did planning at atomic, propositional, etc. But learning, we only did it at this level. Right? Decision trees at this level. Statistical learning at this level. SVMs at this level. Linear regression at this level. So if I were to tell you that you can do non-trivial learning at this level, you should be surprised. Right? And the good thing is reinforcement learning can be done at atomic states, and that's non-trivial learning. Okay? And that basically is, after MDPs, we'll start talking about reinforcement learning, where in fact most of the first discussion will be understood at the reinforcement learning would be understood at the atomic level. And of course, then we will generalize it to propositional and relational, etc. If anything, learning is even better at higher levels. Okay? And what happens in the reinforcement learning is, while the states are indivisible, you have actions working on the states. And you can say, if I am in this state, eventually I'm going to be sunk and fall into an abyss state, a state which has minus infinity reward. So I will be able to look ahead and realize these are bad states. I don't want to get into them. Rather than wait until falling into the abyss and realizing, looks like I have fallen, I shouldn't be falling in this place again. Okay? You want to realize, let me not even get towards the states that will make me fall into the abyss. And how did I get to that state last time around? Well, I was happily here and I did this action, then I got here, then I did this action, I got here, then I did this action, I got here, and then I didn't like what happened to me. So I need to learn and say, don't be here. Or if you're here, don't do this action. That's what reinforcement learning is at the atomic level. And it's non-trivial at the atomic level, and it becomes even more interesting at the propositional level. Okay, so that's the, I mean, there's no way, if you haven't thought about it before, there's no way you would have thought about this right away, you know. So those of you who gave me answers at all, thank you. In fact, I was planning to get some ice cream for the person who actually gave the wrong answer, because wrong answer is better than no answer. You know, no answer allows the palm deepiness. You know, I'm infinitely smart, but I just don't want to open my mouth. You know, so, okay, yes.
And ice cream is better than just thinking about it.
Ah, yeah, well, but you won't get ice cream if you don't think at all. Okay, so anyway, any questions on that? So that's the connection between that little question I had and the bigger picture. If there are no questions, then we will start talking about MDPs. Okay. So MDPs are, so as I said, to repeat what I already mentioned multiple times, we know how to deal with the atomic models, planning in the atomic models with deterministic environments and goals of attainment. Okay, there are lots and lots of things missing from there, but two things that I would like to talk about here. Rewards are only at the end in the A-star search model. This model is A-star search model. Okay, rewards are only at the end, but in life you get rewards all through your existence, and there is no end per se necessarily. Okay, and so how do you talk about reasoning in those kinds of scenarios, in those models? And the second one, first of all, what should be the model which allows rewards to be not just at the final stage, but anyway? Okay, and secondly, the dynamics here have been assumed to be deterministic, but they don't have to be. At the minimum, they can be stochastic. Actually, it's not, at the minimum loss, it will be at stochastic. Even more loss of information, as I said last time, you would go to non-deterministic. And even more than that, you would go to, what do you mean actions? What I have no clue what my actions will do. And even more than that, I don't even know what actions I have, which is what our life is. Most of the time, you don't even know what are all the actions you have. I mean, in the kitchen, it happens all the time. There may be something that you need to do, and you will be thinking, what am I supposed to do to make this happen? And then we will be able to figure out some random action, which, I do have this tool that can be used for this. And even discovering that, is something that we have to do most of the time. Okay? But for now, we'll assume the actions are given, and they're stochastic. Okay? And so you are looking for models which only generalize the A-star search in just two different ways, generalized rewards plus stochastic rewards. That would keep us busy for the next couple of classes at the minimum. Okay, and then those are basically what I call the Markov-Decision processes. Here's a picture which would probably be more easy to understand before we go to the formal definition. As I said, I sent another mail again to the list that I had, but I will, basically the MDPs discussion would be based on the chapter in Russell and Norway, and you should start reading that chapter, so that, based on your faces, I would know whether or not you read. Today, I would, it's fine because some people may not actually have gotten that mail. Yes?
If there are rewards in between, before the goal state, it's quite probable that the agent won't be able to achieve the goal state.
Why?
Because
the agent likes this reward and hangs around here, you mean?
Because then his reward at this particular state will be more than going towards the reward which he will get when he will reach the goal.
No, okay, first of all, again, that's a question of setting up the problem. That's a question of setting up the problem. If I set up my course such that being in this class up to the second day is much more valuable than being in the class all the way to the bitter end, then I would hope that the ASU graduate students are intelligent enough to drop after the second day. Do you understand what I'm saying? But what is interesting is many a time in life, we'll see it here too, there would be, the problem would be, you may actually not, the agent may not be long-sighted enough to see that there is a value.
That is...
Okay, that if you don't see that there is a value, I can't help you. If I set up the problem such that there is no value at the end, you can't help me. Do you see the difference? Okay, if your problem is such that the agent, any half-intelligent agent, should leave right after the first two states, then you should be happy that the agent did that. If your problem is such that, in fact, the agent essentially is taking the first immediate reward it gets and giving up on the long-term reward because it doesn't actually do the reasoning required to figure that out, then you need to improve your agent. Most of what we do in life, especially at least our parents seem to tell us that we are some of these myopic agents. Myopia basically means you focus only on the immediate reward. Okay? And myopic agents apparently we are myopic agents when we are kids. And so your parents keep telling you, hitting on your head, saying, no. Even though watching another Seinfeld episode seems like a particularly good thing to do, there is this exam, and this exam's marks will be added to another exam, which will be added to one more exam, and then there'll be a GPA, and there'll be more GPAs, and in the end, you will be on Mill Avenue asking for money, if you stop out of the school. And so they are able to do this for you. So they are offsetting your myopia, with theirs. If you hopefully figure out how to lose your myopia before coming to college, then it's fine. If not, your parents should be sitting next to you even now. Right? Basically, that is the reasoning, and that's a good challenge for AI.
But to check the efficiency of this algorithm, we should check it with the real world, and it happens most of the time that because there is a lot of struggle and hard work involved in getting the last goal, we just get happy with the reward.
That's not, again, what I'm saying is, we will talk about this. This is MDPs are a great model. Unlike A-star search, which people think, oh, it's obvious, this is graph search, I'm here, it's a connected graph, this is the end of the goal, and I just need to do the actions to get there. MDPs bring in all these issues, but clearly there are answers to that. Okay, so let's look at this. In fact, pretty much the next slide, your answers will come to some extent. Okay, so here is a very simple word. It's a grid word. You can't get here. The agent is here. The agent can do essentially go up, go left, or go right. That's it. That's all. That's the only actions it can do. Okay, and if it, go up, go left, go right, go down. Everything. It can do all four actions. The actions are such that if you are intending to go up, if the agent is intending to go up, it will go up actually with 0.8 probability, go left 0.1, go right 0.1. And the same thing if it's intending to go right. If it's intending to go right, it will go with go right with 0.8 probability, down with 0.1, and up with 0.1. Never goes back. At least that much we put reasonable amount of mechanism in the. Okay, so that's your agent, and here is the start state, and basically, first of all, if this were deterministic, that means if there is no stochastic dynamics, you can model it as A star, right? Okay? It's stochastic, so it's not exactly A star. And the other interesting thing is, I have two states here, +1 and -1. These are 6 states. That means in those states, you can't, if you do an action in those states, you just stay back in that state. That's just part of the transition function. I give you that, yes.
Can I ask a question regarding the problem real quick?
Mm-hmm.
Where A square, you said you can't go in that square. Does that mean there's 0 probability that you'd accidentally go in that
No,
square?
yeah, that basically what it means is when you are here, when you try to go right, with 0.8 probability you'll stay here.
Okay.
That's the way to think about it.
And then
okay?
if you're trying to go up with 0.1 probability.
And down with 0.1 probability. That's a very good question. There's a picture here, but what does it mean you can't go in here? You essentially try to push yourself in there, but then, you just stay here.
Banging the wall.
Yeah, so you're banging against the wall and you stay here. Okay? And so 0.8 probability you will stay here, 0.1 you'll go up, 0.1 you go down. That's your simple model. Very simple model. You can have nice intuitions about it. And then there's +1 and -1. Okay. One other thing I throw in is if the agent is just dilly-dallying, hanging around in a state, it gets immediate rewards. For each state, it gets immediate reward. In fact, there is a reward function. The reward function is +1 here, -1 here, and minus 0.04 for every other state. So as soon as you get into that state, they'll give you a door prize, minus 0.04 for you. just for taking the time to come here. Okay, obviously, this basically is, saying to the agent, move along, because it's a little whiplash, because negative means bad, let's assume that. If you have an agent which likes negatives, we have a very different semantics. Okay, so that's basically my scenario. Clearly, you can see that it's more general than A star search, right? It's more general than A star search. Okay, my first question is, so there is a reward function, and then the fact that these are sync states is part of the transition function. The transition function says, when you are in this state, every action leaves you back in this state. Okay? You can write this down. I mean, it's a small enough word that you can write it down at atomic level. Now, the question is, what's the solution? What are we supposed to solve here? Presumably, the agent is here. Apparently, the fact that the agent is here, it needs to do something to increase its reward. Right? So the question is, in each state, so now here's the other interesting thing. When it is in this state and it tries to, let's say, go up, can it, in its mind, think, where will it be? Not exactly. It won't be knowing unique state where it will be in, because when it goes up, it may be here, or it may be here, or it may be here. So at the thinking time, it only has all these possibilities, no unique states. So thinking is hard in this case. Now again, as you said, if you don't feel like thinking, I mean, if your agent particularly doesn't feel like thinking, then one thing it can do is, come on, this is 0.8, 0.1, 0.1. I'll just assume 0.8 will occur all the time. Okay? And that's not a particularly wrong thing to do. Many of us basically say, come on, they say it's 40 miles per hour, otherwise we'll give you a ticket, but not for me, I mean, there'll be a reasonable amount of probability that I won't get the ticket. I'll just go at 75. Right? Right? Okay, so because most of the time nobody ever gets tickets. So we'll do that, and that's what you're doing. You're going for the immediate thrill of going very fast with the windows up, I guess. In Arizona. But anyway, so this is a way of approximating the problem. Okay? A way of being completely irrational about the problem is to say, well, I will basically say that aspect of the problem will occur, action will occur, which will increase my reward. Okay? Suppose I'm here, I can go to this state, this state, this state. My action model says this is 0.9, this is 0.05, this is 0.05. But I think here I'll get $1,000. Here it's only $2. I'll just assume God is looking after me, so I will just do the action and let's hope that I'll be here. Those people don't exist mostly, except in various fringe areas. Okay? Because that's completely irrational. Just makes no sense whatsoever that the world is out there trying to change its dynamics to suit your pleasure. Okay? So most normal people, I mean, if you have an agent that's going to be intelligent, especially at a graduate level AI course, it needs to reason with these three possibilities. Right? That's what you need to do. So, okay, so what is the solution for this step? What will the solution tell us?
The path to +1.
But what path? So if I, for example, made a very nice path that said, first go up, then go up, then turn, then go. That's my plan. Can I just execute it?
No, because
it may not happen.
It can go somewhere else.
Do you see what I'm saying?
Yes.
So what is your plan going to be?
At each state, it should find out where it needs to go.
So your plan essentially has to be a highly conditional plan which does an action and looks at the word. Does an action, looks at the word. Does an action, looks at the word. Okay? So this is where the difference between stochastic versus deterministic on one hand and observable versus unobservable or partially observable on the other hand comes in. These are totally orthogonal dimensions. I can have words which are deterministic but not observable. I can have words which are stochastic and are fully observable. I can have really bad words which are stochastic as well as not observable. Okay? So in MDPs, the assumption, our model assumption is States are completely observable. So once you get into the state, it tells you, hi, my number is S75. So you know, and so, hey, I'm supposed to be S75, you are S75, so I'll just do the action I'm supposed to do in S75. If it on the other hand says, oh no, my number is S97, then you'll say, I don't know what to do. So really what you should have done beforehand has to have figured out for each state you can find yourself in, what action should you do. Each state you can find yourself in, what action should you do. If it is an ergodic world, which was one of these good things I talked about last time, that means from every state you can reach every other state, except for the sync states. Actually, this is not an ergodic world, by the way, right? These are sync states. Okay, but the rest of this part is all connected. Every other part of the state, except these two, are connected. Because of which, really, you can find yourself in any of these states with some non-zero probability. Which means you need to know what to do in any of those states. So the so-called plan is a highly contingency-oriented plan. It says, if you are in this state, do this action. You're in this state, do this action. In this state, do this action. For every state of the world, it tells you what action you should do. If you have a plan, then that's when you have a plan. If on the other hand, you only know what to do if things go your way, that's the kind of plans we normally have. You know, I just hope things will go well, and if they didn't go well, so I haven't thought about this idea. You see what I'm saying? Okay, so at the when you don't worry about computational cost, the solution for an MDP is a mapping from states to actions. Mapping from states to actions. And these are called policies. So instead of plans, plan is also a reasonable word, but typically the technical word that's used is a policy. So a policy pi maps S to action A. Now interestingly, actually, it's not very obvious that S should be mapped to a single action A. Why not? I have a pi dash which maps S to A1 with probability 0.7, A2 with probability 0.2, A3 with probability 0.1. That's a policy too. That looks like a policy, right? So if I'm ever in state S, I have my trusty coin, three-sided coin. I toss it, okay? It's supposed to come heads with 0.7 probability, tails with the 0.2 probability, and the third side with 0.1 probability. And whichever side it comes, I'll do that action. That's going to be a policy. Do you think those kinds of policies would have to be also considered here? I mean, you can't stop people from doing that, right? I mean, people can say, hey, yesterday I did that action, that didn't really do all that well. Today I'll do a different action. I'll sound much more sort of intelligent kind of a guy because I'm sort of mixing my policies. In fact, this is called a mixed policy. It's called a mixed policy. You need mixed policies. Well, the question then is, can you use mixed policies? Of course you can. You can do anything you want. Your agent can do anything it wants. It can just stop in the middle of a state and start singing. Nobody can stop it. Right? The question is, if you are designing an optimal agent and it is searching across this set of policies, notice the policy is a mapping from state to the action, right? Suppose there are S number of states and there are A number of actions. How many different policies are there? In the first state, it can do any of the A actions. In the second state, it can do any of the A actions. In the third state, it can do any of the A actions. So this is a power S. Number of policies. Now we are talking data structures and computer science. Okay? So if you want to make an agent that finds the optimal policy, all you need to do is look at all these A power S policies and figure out which is the best. Now, of course, it turns out there are two parts to that question. One is look at all the A power S policies. That's easy enough. and 2 is compare 2 different policies. I haven't actually talked to you about how to compare 2 policies. You know, the way it's going, you will probably be talking about it next Wednesday, because there is next Monday is a Labor Day. It's the Labor Day this year. Okay, but you should read ahead. You know, partly what I'm trying to say is that there is a large number of policies, and you need at least one how to compare 2 policies. And supposedly it will be something about policies would be compared in terms of the rewards they accumulated, because that's the only thing that matters. Okay? And the second, of course, is how to find the best policy. The best policy is the one which dominates everybody else in terms of the rewards it collects. And you know, if you are trying to find optimal policy in a space which is a power s, in the worst case you have to do a power s amount of work. Right? And so, you should be really happy that we only do s power n, I mean s power 2 actually, amount of work, and still get optimal policy. Only s square. I mean, the trick about coming up with bad algorithms is to, you know, get people to look for even worse algorithms, and then say mine is not that bad. Right? It's only s square. You thought it will be a power s, you know. So my way of teaching, you know, sorting algorithms for computer science students would start by saying, take any permutation, see if it is sorted. And there are only n factorial permutations. And each one you check if it is sorted or not. And so I have a nice n factorial algorithm already. And then when I give them an n cube algorithm, they'll be happy. They won't be asking me where is the n log n algorithm. Right? Okay. So there is this a power s, and it's actually by the end you'll find out it actually can be done in s square. That's where this beauty of dynamic programming comes in. That's where the algorithms and computer science come in. Right? Now, before I even go there, my question is, can I, since my agents can look at mixed policies, right? Should I be searching in the space of mixed policies?
There would be an infinite number of such.
First thing is there would be infinite number of them. And so, whether if your infinity is at the, you know, exponent or on the base, it doesn't really matter. You're dead anyway. You're toast, right? So the question then is, why isn't mixed policies needed? It turns out there's actually a deep theory. We may not even actually go into the theory part, but it turns out that if you find the best mixed policy, I can then give you a deterministic policy which has the same value. Whatever the measure you're using to compare policies, you come up with your best mixed policy. I'll give you a deterministic policy. These are deterministic policies. That's just as good. Do you understand what I'm saying? So then why must I waste my time looking for mixed policies? Even if you want it, that's fine with me. That's fine with you. But I can only search, I'm only going to search in the space of deterministic policies.
Why in game theory?
Yes. So the question is, when would I be really off my base if I do not do mixed policies at all? As this guy was saying, game theory. Have any of you played rock, paper, scissors? Okay? You know, there is a beautiful Simpsons cartoon that I have seen once. Maybe I'll show it to you next time. Where Bart and Lisa are trying to figure out who's going to, you know, who's going to have to do the chores, like, you know, cleaning up the vessels or something. And Bart comes up with the idea, let's play rock, paper, and scissors. And then whoever wins will win the game. Will have to actually, the other person has to do it. And then on top of Lisa's head is this, on top of Bart's head is this bubble saying, hey, I get to play rock, paper, and scissors. And on top of Lisa's head is another happy bubble saying, yay, we get to play rock, paper, and scissors, and Bart always picks rocks. You see what I'm saying? So the worst thing that you can do in rock, paper, scissors is to have a deterministic policy and let your opponent know that you have a deterministic policy. You see what I'm saying? Because then you won't even draw. I mean, this is a game where you'll not win anyway. Okay? Although kids seem to be playing continuously. You can't win, but if you have a deterministic policy, as somebody said, just because there are no good ideas doesn't mean there are no bad ideas. Okay? There's no good way of winning rock, paper, and scissors, but there are many ways of losing it. One of which is to say, I really like rock. Then you're dead. that's your answer. That's what I think the gentleman is trying to point out, that when you have other agents, you need to search in the space of mixed policies. So you can only be happy for the next couple of days when you only need to search in the space of deterministic policies. There are only exponential number of them, and then we will show that in fact it's actually possible to find the best among them in polynomial time, which is not surprising. I mean, there are exponential number of permutations. I find the best sort in polynomial time. So, not every problem will have that structure, but this problem has this beautiful structure. Dynamic programming algorithms can be used. Okay, so I unfortunately have to stop here. I think actually maybe next slide I have 1 minute. And that would actually be a useful slide to end with. And then next class, please read the MDP section, and then we'll discuss the algorithm. Okay, in this, the interesting thing, this is actually directly from the textbook, so you can go slowly on it after this class. But essentially, just by keeping the dynamics exactly the same, but changing the rewards, I can change the optimal policy like completely. Which is not surprising, because in fact, you may have heard of the word mechanism design. Mechanism design is the design I make about how to make my course such that I optimize your behavior if you use your brains. So this is what we were discussing earlier. If I make my course such that it's in fact optimal to drop it after the second day, which actually it is, because then I get to teach much fewer people. But if I do that, then I shouldn't be complaining that everybody dropped after the second day. Right? So the mechanism design is reward structure. What rewards do you put such that people do the right thing? What incentives do you put? So typically, your kid does not understand 10 years from now, they will not have to, ask for, loose change on Mill Avenue. They just don't understand that. So you say, well, if only you study for another hour, I'll give you a really big cookie. And, they might fall for that. Okay, so this is actually the optimal policy for this particular problem. When you have -1 sink here, +1 sink here, and every other state it's -0.04. In that case, if you are ever in this state, the optimal thing to do is go up. If you are in this state, go this side. If you are in this state, go this side, etc. Okay, that's the optimal policy for this. First of all, think about whether or not it makes sense. The thing now I'm going to do is just by changing the reward numbers. Remember, all the states have the same reward except these two, and they were all -0.04. Suppose I just change it to a slightly different number. Suppose I change it into -1.6. That means every state has higher negative reward than debt. What looks more appealing to you then? Death. Right? I mean, you're intelligent. I mean, again, people who are depressed are intelligent. Please understand that our brain still works. Okay, it's a beautiful machine. And the problem is your reward structure is all messed up. And so you really think there is no point, because tomorrow is much worse than eventual death. So I want it right now. The eventual death right now. Okay? So if you do RS less than, reward less than -1.6, your algorithm, just the same algorithm that you would be using for finding the optimal policies, would give you this as the optimal policy. If you're depressed, that's the optimal thing to do. Or you go to your psychiatrist who changes your reward metric by pouring lots of medicines. Okay? So in this case, notice that if he's here, it goes there. It goes here, it goes there. Anyway, just end it up. The important thing is ending it. Because you might say, why is this agent going in here? Because it too ends it. Ends it with positive. This is ends it with negative. Okay, I guess maybe this is the cyanide and this is bullet in the head. Okay? But still, ends it. Okay, and that's interesting that a simple algorithm called value iteration that you will learn about will do this. Because this is what your intuition says, and that's what we'll do. Okay, whereas if the RS is somewhere in between, it's slightly different. It's in this range, it's somewhat different. You should actually look at it to see whether your intuitions work fine. And the best is, if the reward for hanging around in the states is high. Right? Right? I mean, it's like, you know, if you're in a grade school, they will have courses, and then you will have to walk between courses. You have to walk through to get to the next course, and they'll play this music. Suppose that music is so beautiful, then it's really heck with the course. I'll hang around listening to the music. Right? Then whose mistake is it? It's not the agent's mistake. Agent knew exactly what's the right thing to do. So in this particular case, if RS is greater than 0, the optimal thing to do is to do anything other than dying. Anything other than dying. So people who believe that life is fun make very, very bad parishioners in your church. Because if you're a priest, you're saying, you know, if you're not nice, when you die, all sorts of these things happen, you need to plan for it, and you're saying, I'm having so much fun. Let me just avoid church directly. You know, because that's bad news. Okay? Again, just by changing the rewards. Now, for a given problem, maybe rewards will come pre-packaged. But you also get to mechanism design. And if you mechanism design your classrooms, walking around, such that you put very beautiful music, and you put cushy chairs in between the classes, and you're wondering why aren't the students coming into the classes? The joke is not on them, but on you. You who designed the reward mechanism. Okay, so that sort of answers to questions. Okay, now the interesting last part is, even when you have reward structure like this, an agent might say, hey, you know, I feel like going in here. Let's see what happens. You know, it's like all the people who fall off Grand Canyon, thinking Grand Canyon is a place to fall off rather than to watch, they're not all depressed. They just have basically mentally challenged. You know, it's a fine line. Okay, they don't use their inference mechanisms. They think, you know, if other people fall off, not me. You know, I'm sort of more superhuman. So let me just take one more, two more steps to get a really good angle, you know, of my face for my photo, and then I will be done. Okay, right? Now, in that case, the reward metrics were fine. It's just that the agent decided not to use the model correctly. Then you change the agent. Or you say this is just neural Darwinism, you know, the pool of people, agents left are better agents because they're not falling off of, you know. So we'll stop here. As you can see, even at the atomic level, MDP is a much more fun model. Imagine having this kind of a discussion for A-star search. You know, here is a point, here is another point. Notice this path versus this path. You can't have anywhere near as much of an interesting discussion. That's why this is a more interesting model. Okay, so we'll talk about how to find optimal policies for this.